Yeah, so day before yesterday I participated in GFG's Job-A-Thon hiring challenge, and today I'll be explaining my solutions to the coding problems. So let's move on to the first question. So the first question is subsequence max, and here we are given an array of n integers, and we need to choose a subsequence from the given array such that max of the chosen subsequence is maximum. Similarly, the length of the subsequence should be as minimum as possible. And let's see an example. So in this case, the maximum x possible is 3 in the array, and the subsequence with minimum length having maximum x is 1, 2, 0, 1, 2, and 0. Similarly, in this example, the maximum x possible in the whole array is 0, and the subsequence with 0 as max is the empty subsequence here. So the constraints are n can be up to 10 power 5 and ai can be up to n only. From 0 to n ai can be. So let's see how to solve this problem. So first, before solving the problem, let's see what a subsequence is. So subsequence is nothing but it's a subset of a sequence that's called a subsequence. In this array you can see there are also so for an array of length n, there can be up to 2 power n subsequences. So we need to choose one such subsequence which has the maximum max, and we need to return, and it should also have the minimum length among those subsequences which has the maximum max. Okay, so let's see what max is. So if we have an array 1, 2, 3, and if we have an array 1, 2, 3, and we need to find the max of an array A. So max of an array A is defined as the minimum excluded element, which is nothing but the smallest non-negative integer which is not present in this array. So as you can see here, the smallest non-negative integer which is not present in this array is 0. So we will return 0 as the max of this array. If 0 were to present in this array, 0, 1, 2, 3, in that case the smallest non-negative integer which is not present in this array would be 4. So in that case, max of the array will be 4. So similarly, we need to, among those 2 power n subsequences, we need to first find the maximum max, and we need to find those subsequences which has maximum max and get the minimum length among of those subsequences. So this is the problem, and so the first thing to note here is n is up to 10 power 5, so we can't use any brute force or n square solutions. So the expected time complexity would be around order of n or order of n log n. So let's make few observations to solve this problem. Okay, so let's take this example. So here you can see they are saying the maximum x possible is 3. So let's examine how it's possible. How is it coming 3? Okay, so if you take the whole array, you can see here 0 is present in the array, 1 is present in the array, 2 is present in the array, but 3 is not present in the array. So which means whichever subsequence you take, the maximum max you would get won't be greater than 3. So the first observation is if the first non-negative integer which is not present in the array would be the max of the whole array. So in this case it's 3, so the maximum value won't be greater than 3 for any subsequences. So that's the first observation to make here. And similarly here you can see 0 is not present in this array, like how 3 is not present in the previous example. Similarly 0 is not present in this example, so the maximum max possible is 0. That's what they're saying here. Don't see this value, see this value, this is the max. Output we are returning the length and not the maximum max value itself. So we also need to note that we need to return the minimum length and not the maximum max. Okay, so this 3 represents the minimum length of the subsequence, and similarly 0 here, and this 0 and this 3 represents the maximum x value. So let's see how is it possible. From the first observation itself, we can see that if we take the whole array itself, we will get we can achieve the maximum x, right? Because the whole array itself is a subsequence. Among those 2 power n subsequences, the whole array itself is a subsequence, is one of the subsequences. So if we take the whole array, we will still get maximum max as 3, but we need to find the minimum length of such subsequence. So we need to check if we can do better, if we can reduce the length of the subsequence and still get maximum x is 3. Okay, so let's see how to do that. Okay, 1 2 1. Okay. Let's write the first example. A is given as 1 2 1 2140 2140. Okay, so if we take the whole array, the max of the array would be 3 and length of the array is 7. So 7 is maximum, we need to reduce the 7. Let's see how to do that. So as the definition of max goes, it is the smallest non-negative integer which is not present in the array, right? So can we try to just manually find a subsequence which has max 3? Like we can find out few examples and then we can see if we can make another observation or not, right? So let's see. So in order for max to be 3, 0 has to be present in the array, right? So let's pick up 0. Similarly, in order for max to be 3, 1 has to be present since 0 is already present. So 1 has to be present. Okay. So similarly, to reach 3 we need 2 also. Okay. So we got 0, 1, 2. Okay. But we can also have extra values, right? It doesn't matter. Like if we have an array like 1 2 1 1 0, we'll still have max as 3 because max is just smallest non-negative integer which is not present in the whole array, right? So 3 is not present in the whole array. Okay, but the length of the array is 6 in this case, 6. But if we just pause for a moment and think about the previous subsequence which we chose, which would be, let's call it a dash, should be this 0, this 1 and this 2, right? That's what we chose before. So this would be a subsequence. A dash would be 2 and 0. So here you can see even this is a valid subsequence having max as max of a dash as 3, but the length is 3. But the length is 3 here, which is smaller than both of the previous subsequences, right? So now we got a the most optimal solution here in this example. So similarly, for among those two power n subsequences, first we need to find the maximum x possible, and then we need to find a minimum length of those subsequences. So as I said, the first observation here to make is maximum max of any subsequence will be less than or equal to the max of the array. So in fact it will be for this problem, the optimal way to choose such subsequence would have maximum max as equal to the max of the array. So only then the first thing to do in the problem is to maximize the max, right? So if we don't maximize the max, there's no point in, we won't get the optimal solution. So the first subsolution here to make is maximum max of any valid subsequence which can be considered as a valid solution should have its max equal to the max of the array. Okay, so now we have reduced the total number of subsequences from 2 power n to some few subsequences which has the max equal to the max of the array, right? Okay, first part of the problem is done, which is maximizing the max of the such subsequence, which will be equal to 3 because it can't because subsequence is a part of an array, right? So it can't have a max greater than the array itself. So that's the first thing. Second thing is we need to minimize the max. So when can we minimize the max? So as you can see here, both of these subsequences, both of these arrays has the same max value 0, which is 3, but their lengths are different. So how is that possible? Okay, so here you can see this array a dash only contains unique elements and a contains few duplicate elements. So that's another observation to make. Like if we just take any such subsequence, any valid subsequence, and remove all the duplicates from them, we will get another subsequence with minimal possible length but with the same max, because we are just removing the duplicates and not the entire values itself, right? So in this case we will just remove these two ones and we'll keep 2 1 0 as it is. So in that case, from this a array we will get this array a dash array. Okay, but this A dash array itself is a subsequence of the given array A. So why choose a subsequence which has duplicate elements when you can easily find a subsequence which has unique elements? Because we just came to know that after removing the duplicates, the max of the subsequence won't change, right? So before when finding the subsequence itself, we will try to find the subsequence which has only unique elements. So in that case what will happen is we will have a shortest possible subsequence with the given max, right? So here it will be 1 2 0. Okay, so how do we find the subsequence in optimal time? Like, we can't go through all the subsequences and find, right? So how do we find them? Okay, so in order to find the duplicate, in order to eliminate duplicate elements and still have an excess 3, what we can do is first we can sort the whole array. So after sorting the array, let's just sort this array. After sorting the array, A will look like, let's call it A double dash. A double dash will look like 0 1 1 1 1 1 2 2 4. Okay, let me just erase. Yeah, after sorting the array, the new array will be sorted array will look like this. And here you can see, here if you try to find the subsequence with maximum max, it will be 0 1 and 2 directly. We won't bother to care about the duplicate values, and we don't need to worry about 4 also, because 3 is not here. So since we already know the maximum max, which will be 3, we will try to find a subsequence which has this max, right? But we can easily do that, because since we know in order for a subsequence to have max 3, it should first have 0, it should have 1, it should have 2. Only then the max of that subsequence, it must have these 3 elements, at least it should have at least 1 0, at least 1 2, at least 1 1. Only then it will have maximum excess 3. So we'll try to do exactly that. Here we'll try to find that exactly here, and if we do that, we'll get the maximum excess 3, right? Let's see how. So first we need to find 0. Okay, since we sorted the array, all the values will be in increasing order, right? So we can easily first find 0, and then we can find 1, and then we can find 2, and then we will get 3, because we already know it is guaranteed that the max of the array will be 3. So it's guaranteed that we will be able to find the value, but we just need to find the minimum length, right? Minimum length is when we just print these 3 values. If max is 3, the minimum length would be just 3 only, I think. Yeah, like if max is 2, 0 and 1 should be in the array, so we'll just take to 0, 1, because we already found the max of the array as 2, right? So 0 and 1 should be there. That's why we got max as 2. So hence the length of the minimum subsequence which has max as 2 would be 2. Similarly for max as, let's say, 5, we must have met 0 1 2 3 and 4. Only then we would have got max as 5, right? Even if we meet only then we would have got 5. So once we find the max, we can directly say that the maximum, once we find the max, we can directly say that the minimum length of the subsequence which has max is max itself, which is minimum length will be equal to max itself. But in order to do that, we first need to find the maximum max, which is just, as I said before, the max of the whole subsequence itself. So in order to find the max of subsequence in optimal way, so the optimal algorithm will run in order of n log n time, because if the input array is not sorted, we need to first sort the array, and then we can keep a variable called max to find the max in linear time. So if the array is sorted, we can find it in linear time, but if the array is not sorted, we need n log n time. So let's see how we can do that in code. Okay, so yeah, so as I said, first this is the input array given here. First we sort the whole array, and then we keep a variable called max, which will be 0 initially, which will be assumed 0 initially, and then we'll traverse through the whole array. As soon as we find an element with the current max value, for example, as soon as we meet a value, initially max was 0, right? So as soon as we meet 0, we will increment max to 1. As soon as we meet another value, we will increment max to 2. Now when I meet 2, I will increment the max to be 3, and when I meet 3, I will increment the max to be 4, but there is no 3. Hence, after we traverse the whole array, our max value will be still 3, and we can easily return that, since we saw minimum length will be maximum max only. So we can just return the maximum max itself, max of the whole array itself. So in the end, the problem just reduces to finding the max of the whole array. So that's the first problem. On the time complexity will be order of n log n, as you are sorting the array and traversing the whole array once, and space complexity will be constant space, because we are not using anything else apart from the given array. Yeah, so this is the first problem. Let's move on to the second problem. Okay, let me just remove this. Yeah, so the second problem says again permutation, and here too we are given an array of n positive integers. We have to note that we are given n positive integers, and we need to find total number of subsequences of the given array such that the chosen subsequence represents a permutation. Okay, and as the result can be very large, you should return the value modulo 10 power n plus 7. Okay, so since, as we saw before, there can be up to 2 power n subsequences. So 2 power n with n as 10 power 5 can be very large. That's why we need to take modulo. And another term which comes in this problem is permutation. Let's see what a permutation is. Okay. So in permutation is defined as a set of values. Permutation of length n is nothing but the values from 1 to n. That's it. And the order doesn't matter, but the sequence should contain all the values from 1 to n in any order. That's the definition of permutation. But okay, so we need to count those subsequences which represents a permutation. Okay, so for a sequence of length n, there can be up to 2 power n subsequences, and among those 2 power n subsequences, we need to find those subsequences which are permutations. Okay, so let's see another example for a permutation of length. Let's see an example for permutation of length 5. So permutation of length 5 can be 1, 2, 3, 4, 5. Right. So any arrangement of these values will give a permutation of length 5. Right. So it can be 3, 5, 1, 2, 4. This is also a valid permutation of length 5. So we need to find all the subsequences which represents one of these permutations, like any permutation of length I. Right. Permutation of length I. So where I can be from 1 to n. So that's it. The problem reduces to this thing. And the first observation, okay, let's just see the examples here. Okay, the first example we are given is 1, 2, 3, 2, 4, and the answer given is 7. So 1 itself is a permutation because it has all the elements from 1 to 1. Similarly, 1, 2 is a valid permutation because it has all the elements from 1 to 2. Similarly, 1, 2, 3 has all the elements from 1 to 3. So similarly, 1, 2, 3, 4 has all elements from 1 to 4. So these are valid permutations. 1, 2, 1 with this 2 is another subsequence. That's why 1, 2. And the first 3 values together forms 1, 2, 3. Similarly, 1, 3 and 2 along with this 3 and these 2 forms another permutation, 1, 3, 2. They are just sorting it and representing it again as 1, 2, 3. So that's another valid permutation. And similarly, the 1, 2, 3, 4 is a valid permutation, and 1, 3, 2, 4 is another valid permutation. So basically here they are sorting all the permutations, and like if you take this permutation and if you sort this permutation, you will get this permutation, right? So So first they're getting this permutation and then they're sorting it and then just they're displaying it here. That's why it's like this here. So in the end we have 7 permutations, right? We just need to count the permutation and not print them or anything. Similarly here you can see 1 and 1 comma 2 and this one with 2, this 2 forms 4 permutation, and n is again up to 10 power 5 and a can be only up to n. Okay, let's see how to solve this problem. So yeah, so similarly you can see the permutation of length n should strictly have all the elements from 1 to n, right? So there is no room for any other elements to be inside the permutation. So from that we can observe that a permutation of length I should have unique elements. So that's the first thing. But is this enough to identify a whole permutation from a subsequence? Let's see another example. Let's call an array A as 5, 6, 7, 8. Right. So you can see here the length of the array is 4 and it has all unique elements, but this is not a permutation, right? As I said before, permutation of length I is defined as all the elements from 1 to I. So it doesn't have all the elements from 1 to instead it has all the elements from 5 to 8. So it's not a permutation, right? So the second you can say property of a permutation would be that it should have all the elements from 1 should have all elements from 1 to I. So that's the second observation, which means the subsequence should start at 1. Like the subsequence should have 1 somewhere and it should have all the elements from 1 to I, like in some order. The order doesn't matter, but it should have all the elements from 1 to I and only those elements and not any other element, right? So let's take another example. Let's say let's call it B. If B has 1, 2, 3, 4, 5 and then 7, is this a valid permutation? No, it's not a valid permutation, because even though it has all the elements from 1 to 5, it doesn't have 6, right? Because the length of this array is 6, so it should have all the elements from 1 to 6, but it doesn't have 6. Instead of 6 it has 7, so this is not a valid permutation. So similarly we need to take care of two observations. One is it should have unique elements, and the second property is that it should have all elements from 1 to I and only those elements and nothing else. So using these two properties we can easily count the 2 power those subsequences which has these values, right? Let's see how. Okay, so let's see how we form permutation. Okay, so initially as per the definition, permutation of length 1 is 1 only, right? So we can easily count this permutation in the given array, right? We can go through the whole array. We can just count the total number of ones in that, and then we can easily say that okay, we have like x number of permutations with the length 1, right? But what about the permutations with the length 2? What about them? So the permutations with the length 2 should have 1 along with the 2, right? So we need to find the permutations, find the total number of, first we need to find ones and then we need to find 2 also. So how we can do that? We can go through the entire array, take all the ones, take all the 2s, and then we can group. Let's say we have x number of ones and then we have y number of 2s. We can easily group each one with any of the y's, right? So totally x power y of the permutations are possible. So what about permutations of length 3? We take all the ones, we take all the y's, and we take all the, so x is ones, y is 2's. Similarly we need to take 3 also, right? Because permutation of 1, 2, 3, 1, 2, 3. permutation of length 3 will have 1, 2 and 3 in it. So we need to find, let's say z is a set of all 3's. We take all the values and then, so total number of permutations will be just the product of these values. But you can see here, just doing this manually, like how I said, is not possible because of the constraints, which is up to 10 power 5. So we can't just go through the entire array for each length, like each and every time, and check and count the products, right? So, but the way I have written, we can observe something here, like for the length 1 permutation, this is the length 1 permutation, length 2 permutation, this is length 3 permutation. For length 1 permutation, we took all the ones. Okay, that's a valid case, because we need to find first of all, to form a permutation we need 1. Surely we need 1, so we can't avoid this step, so this step is inevitable. Okay, so what about step 2? Step 2, do we need to again find those ones? Because we just found those ones in the previous step, right? So there's no point in recalculating it again. We can just take them and multiply it here, right? Okay, now we have xy. Similarly, for length 3 permutations, we still need to find the set of 1s and 2s again and again in each step. No, right? Because in the previous step itself we have the set of 1s and 2s, so this is redundant. So we can take those sets and multiply it with the current set of 3s. So you get the idea here, right? Like there's no point in recalculating them again and again in each iteration. So once you find all the subsequences which has 1 in it, you can use those you can take all those subsequences. Let's call S1 as let me define it formally. Let me define S1 as the set of subsequences which ends at 1, right? Similarly, set of subsequences which end at 2. In order to find S2, what we can do is we can take all the subsequences which ended at 1 and we can add a 2 to it to form a valid subsequence which ends at 2, right? Similarly, if we have multiple 2's, we can do the same process I just said now for each one of them, right? So we take all the subsequences which ended 1 and we just add 2 to it, right? Similarly, for subsequences which end at 3, we take all the subsequences which ends as 2 and add a 3 to it, right? Similarly, for subsequence of length 4, we take all the subsequence which ended at 3 and add a 4 to it, so that it will become a subsequence of length 4 which ends at 4. So this is the exact logic we'll be using to solve the problem. Like take first finding the, so you can see here this S1 behaves as some sort of base case to this problem. So using this base case, we just form the solution one by one in each step, right? So this pattern somehow resembles a dynamic programming solution. So we can define a state of the dynamic programming solution, like dp of 1 would be dp of let's say, okay, so let's first define what dp is. Okay, so dp of i will be total number of subsequences ending at I, right? So yeah, so which means as per the definition, the total how we can find the total number of subsequences ending at I, ending at any value I here. So what we did was, in order to find the subsequence of set 3, we took the subsequences of set 2 and added a 3 to it, right? So this is nothing but dp of I will be just dp of I will be, one second, let me just write it cleanly. So the state dp of I is equal to total number of subsequences ending at I. Okay, the base case will be, base case is when dp of 1, dp of 1 is nothing but total number of subsequences which ends at 1. So this will be just we can directly count, like if we meet a 1 in the array, we can directly increment the value of total number of subsequences which end at 1, right? Because all the ones individually form a subsequence. So for example, if we have an array 1 1 2 and we need to find total number of subsequences which ends at 1, here we take this one. Okay, this one itself is a subsequence which ends at 1. We take this one, even this one itself is another separate subsequence which ends at 1. So in that case, base case will be dp of 1, and the transitions will be like how the transitions happen here from one state to another state. We saw before, right? From state 2 to state 3, how the transition happens. We take all of those values and we just for each value in the for each 3 we just add all the subsequences in this length, right? So how to find all the subsequences here? Using dp of I. dp of 2 will represent all subsequences which end at 2, right? So we take all those subsequences and for each 3 we add all those subsequences here. So dp of I will be nothing but dp of I will be dp of I minus 1. But this is this correct? This is not correct, right? Because there can be multiple 3s in the array. So for each of them we need to take all the subsequences which ended at 2 and we should add them to the current subsequences, right? Let me again give an example for that. Let's say we have this array, right? And in this case dp of 1 will be, as I said, it will be 1 because there is only one in the subsequence. And dp of 2, when we come to dp of 2, what we will do, as per this definition, we will take all the subsequences which ended at 1, which is 1, and we just assign it to dp of 2, right? Okay, when we come here again we will do the same thing, but you can see here in that case the dp of 2 will be still 1, but total number of subsequences which end at 2 here is 2, 1 2 and 1 2. So we are doing something wrong here, right? So what is it? Instead of just taking all the subsequences which ended at 1 and adding it to the current value, we are just assigning it here. So we need to add it to the current subsequence. So that's the important thing here. Instead of assigning it, we need to add it to the current subsequence. So dp of I will be dp of I minus 1. So yeah, so this is the this is the subsequence, and the answer is just all the permutation, all the subsequences which are valid permutations, right? So we need to consider all lengths of permutation. So answer is sum of dp of I that I equals 1 to the n. So this is the answer. So this is the transition. dp of I is dp of I. Can write it as dp of I as dp of I plus dp of I minus 1, and the base case will be dp of 1, which will be just a count of 1 in the array. We can just either we can directly find it first and then start the iteration from dp of 2, or we can just go along with in the given order itself. So it doesn't matter. So yeah, so this is a dynamic programming solution. And in order to correctly find all the subsequences, we need to do one more thing here. You would have noticed here that we found 1 3 2 4 as another subsequence which is a valid permutation, right? So you can see here 3 is before 2 in this subsequence. So if we use the same logic we use here, what we will do here is, after seeing a 3, we will say, okay, how many subsequences we have which ending at 2? Only 1. So we add 1 2 3, and when we see 4, we'll ask how many subsequences which end at 3, only one, so we add 1 to dp of 4. So in that case we'll be having only one subsequence of length 4, but which is wrong, right? Because we have another subsequence also, which is 1 3 2 4. So this 2 is somehow not getting into the subsequences of 3. Why is that? Because as we see here, we are defining dp of I as dp of I plus dp of I minus 1, right? So we need to find all the subsequences which ends at which ends at I minus 1. Only then we can find this all valid subsequences which end at I. So in order to find all the subsequences which end at 3, we should find all the subsequences which end at 2 before coming to 3. So we can't miss any subsequence, right? So here if you see, we are missing the subsequences which end at 2 here, because since we are after reaching third index, we are missing out the subsequences which end at this 2. So we can't afford to have that, right? If we do that, we can't count all the values. So in order to deal with this case, one of the possible solutions would be just to sort the array, right? So if this 2 comes before this 3, then we would have already found out the total number of subsequences which ended at this particular 2, right? So using that, we can find in that case 3 will be here, so we can easily find the dp of 3, because since we have already found out all the dp of 2s before reaching 3. So in order to do that, the first thing to do again in this problem, similar to the previous problem, is sort the array and then apply the algorithm, right? So let's see the code. So code is pretty simple, as I said before. The first thing to do is sort the array, and then since we need to take mod, let's define the mod as well, and then dp of n plus 1, because the given array can have up to n, a can be up to n, so dp of n, we will define the size as n plus 1. And so this is as I said before, like either we can first compute all dp of 1 and then start with dp of 2 and then compute, or else this is an like you can say like a hacky way to deal with this case. If we just set dp of 0 to be 1, you can whenever you encounter 1, you will do dp of 0, right? Because dp of I is defined as dp of I plus dp of I minus 1. So if you set dp of 0 as 1, so for each count of 1 it will increase the dp of 1. So this is another way of doing it, but you can also do like I said before, you can count all the ones first and then start with the 2 and then continue the process. So this is one way of handling that. And then since the array is sorted, we can easily use the transition I said before, which is dp of I equals dp of I plus dp of I minus 1. Using the transition also, we should not forget to take mod, and then answer is just for computing answer, as I said before, answer is the summation of dp of I from 1 to n. 0 won't come into this place because permutations will start with 1 only. So so the answer will be summation of all the dpi, and we can return the answers. That's it for the second problem. So let's see the third problem, right? So this is an interesting problem. The accuracy is very low, but let's see how to do this. So cars on tree. In this problem, we are given a rooted tree with n nodes from 1 to n, and the tree is rooted at 1. The tree is rooted at 1, and don't see this line, because in the problem it's already actually the root can be any value, not necessarily 1. So next, there can be infinite number of cars present at root node. So we have a rooted tree. And there can be infinite amount of cars present in the root of the node, root of the tree. and each of those car can have a k units of fuel initially. Okay, so each of those car can have k units of fuel initially, and each leaf node has an infinite supply of fuel. So leaf nodes are these nodes which doesn't have outgoing edges. They are leaf nodes, and they have infinite supply of fuel. Okay, and a car from a node can travel to any of its adjacent node in 1 unit of time, consuming 1 unit of fuel. Okay, so if we have a car here, it can travel via an edge and reach another node by spending 1 unit of fuel. So this is another thing, and also time which will be spent is minus 1 second. 1 unit of time we can say. Okay. And next thing is also more than one car can travel on a single edge at a given instant of time. Okay, so since we have infinite number of cars here, so any number of cars can travel through this edge at any moment of time, at a single time. So that's another case. And whenever fuel tank of a car becomes 0, it can refill it from any one of the leaf nodes present in its subtree. Okay, what is it? Let's say our car is here, and so as we see here, whenever we move from one node to another node, fuel will get reduced by some amount, right? So if we make only one movement, fuel will get reduced by 1. So if at some case after reaching a node our fuel reduces to 0, let me draw another example. Right. Okay. Let's say after reaching this node, the car's fuel gets 0 after reaching this node. From the route it travels here, and the fuel becomes 0. What can happen is the car can refill its fuel tank by requesting some fuel from any of its leaf node in its subtree, right? So the subtree is nothing but the whole tree along with the current node as root. The whole tree is a subtree, and it can refill its tank by taking some amount of petrol from any of its leaf node, right? So currently this subtree has this subtree has 3 leaf nodes, and it can request for refillment from any of its leaf node. So that's another thing to note. And any amount of fuel can travel from leaf node in a single drop. Okay, so when requesting for refill, after requesting refill, the leaf can send any amount of fuel in the edges, through edges. Okay, and it will however take 1 unit of time for the fuel to travel from node to its parent. Okay, so similarly for the car, it will take like how it took 1 unit of time to travel between 2 nodes, it will take the same amount of time for fuel to travel between 2 nodes, from leaf to its parent. From leaf node to its parent node, it will take 1 unit of time, and similarly for other nodes as well. And then after node got the fuel from the leaf, the process continues and car proceeds to leaf. Yeah, so this thing, so the given process till now will happen forever, and the cars will try to move forward in the tree, right? And then what will happen? Yeah, so what we have to do here, we are given n vertices, n nodes, and fuel capacity of each car initially, and parent array pair of size n, where pair I represents the parent of vertex I. If parent I is -1, it denotes the root of the tree. Okay, this is just a input array of representing tree. If parent of I is 0, if -1, which means I is the root node of the given tree. And what we have to do is we have to find the minimum amount of time after which each leaf node contains a car. Okay, let's see what it is. So let's see, this is our tree, right? And we are given that we have n nodes in the tree. We also know the root node. We also know that there are infinite amount of cars in the root node, and we also know that the capacity, that initially all cars have k units of fuel in them, okay, and we need to find what is the minimum time it takes to reach all what is the minimum time it takes for all the for each leaf node to contain a car, right? If we take all the leaf nodes in the tree and we need to compute the minimum time it will take for all leaf nodes to have at least one car, yeah. So let's see an example case, like let's see, since we have infinite number of cars, we can't just process all the cars, right? So let's take how many, 1 2 3, so since we have 5 leaves, let's take 5 cars. So we can reduce the problem as the minimum amount of time it takes for 5 cars to reach its respective leaf, right? So one car will reach the leaf in this way, another car will reach its leaf this way, another car will reach its leaf here, similarly another car will reach this leaf, similarly another car. And we need to find, so in order for this car to reach this leaf, it will take some t1 amount of time, right? T1 amount of time. Similarly, to reach this leaf, t2 time, t3 time, t4 time, t5 time, and we need to find the minimum time t, such that our leaves will have at least one car, right? So okay, then we just need to compute the times, right? So since we need to find the minimum amount of time, we need to compute. So this problem statement is quite big and it has a lot of details, right? So one of the ways in which we can view the problem is, instead of seeing the problem from the car's point of view, if we just see the problem from leaf's point of view, the problem will get reduced by a lot, right? The size of the problem will get reduced. So if we see for each leaf, if we just see, so what time a car will reach, what time it will take for at least one car to reach current leaf. Okay, let's take this leaf now. Let's say this is the leaf L1. So if we see from this leaf's point of view, we need to find the earliest time in which a car will land on this leaf, right? Similarly for all leaves. So how to find? Okay, so we are given that the car will move from root node to its child nodes, right? So let's see, this car moves to here. So in order to reach this leaf, this car should move from, let me take another car. Yeah, in order to reach leaf L1, the car, let's say call the car C1. This car should first reach this node, and then this node, and then this node, right? So it should take 1 2 3 steps in order to reach this node, okay? But it's not just that, right? Because as soon as it makes a step, its fuel gets reduced by 1. Also the time increases by 1. So if at some point the fuel of the tank becomes empty, it needs to request for refillment and then get refilled and then again start moving, and the whole process continues again and again, right? So if let's say if we have infinite amount of petrol, in that case the time it will take for L1 leaf node L1 to have at least one car C1 will be just the distance between the root node, right? Distance between L1 and root, right? Because if this car were to have infinite amount of petrol, it can easily make 1 2 3 steps and it can easily reach the leaf. Similarly for all the case. So if we let's just initially assume that all cars have infinite amount of petrol. In that case, L1 will have in this case L1 will have a car at 3 in 3 units of time. L2 will have 1 2 3. Similarly L2 L3 both will have in 3 moment of time, and L4, the leaf 4 will have a car in second unit of time itself, right? Similarly 1 2 3 L4 L5 will have 3. So you take all the values and we need to say when what is the moment of time after which all leaves will have car, right? So after second only leaf 4 will have a car and not leaf other leaves, right? So it takes at least 3 units of time to get a car in the other leaf, so we should say 3 as the answer, because after 3 units of time all leaves will have a car. So the minimum answer would be maximum of TI of all leaves, maximum of these values. So first we need to observe this thing, right? Once we see this, okay, let me just clean it up a bit. Yeah, so this is for the infinite petrol case, right? But in the problem we have only limited amount of petrol. Initially it starts with k unit of petrol and then it requests for refillment and then it gets filled again and so on. Okay, now once let's say the car reaches here and it gets out of diesel and then it requests for refillment, what will happen now? Some amount of petrol from some leaf will go to the car and then the car will get refilled, right? Now the question is how much amount of petrol, how much amount of fuel the car can hold. Okay, so in the contest what I assumed was like it can have, initially it starts with k unit of fuel, but then it can have, after which it can have can hold up to infinite amount of fuel. But that's not the case because it's not mentioned anywhere in the problem, and I assumed so, and I got a you can say wrong answer in the problem before. So that's not the case. So after getting a wrong answer, I realized that the capacity of the tank is k. So during refillment it can only get refilled up to k amounts of fuel. So that's another thing to note here. So let's say this node requests this node car here requests for refillment, and any leaf can send refillment, right? Any leaf can send any amount of fuel. But what do we have to find here? We need to reach the leaf node as soon as possible, right? So if we get out of fuel, we need to get the fuel as soon as possible. So what is the optimal way to get a fuel as soon as possible, right? So for that case, let's look at another car. Let's see C5. C5 is this car. Let's say after reaching the second node it gets out of fuel. So among the leaves in its subtree L4 and L5, which leaf do you think is optimal to get fuel from? Is it L5 or L4? If you ask for fuel from L5, it will take 1 to 2 seconds to come to reach the car 5. If you ask for fuel from L4, it will take only 1 second to reach. So it's always optimal to ask refillment for the nearest leaf node, right? So if you have like n number of leaf nodes in your subtree, you need to find the shortest in the nearest leaf node and get the refillment from that node, because any leaf can send up an infinite number of amount of fuel, and it will take 1 second to move the fuel from one node to another node, one edge, right? So for that we need to only because of that we need to find the nearest leaf node and then take the request refillment with that node, right? So whenever we get out of fuel, we just go through the subtree, we find the nearest leaf node, and we request for refillment. Okay, so all this is good, but let's see how to actually get the answer, right? So in order to find the minimum time, we need to, each car should reach the leaf node, right? So let's take the same. Right. So let's say k is 2. Let me add on one more node, right? Okay. Yeah. Let's say k is 2, which means initially all cars have two amount of 2 unit of fuel in its tank, right? So in that case, let's look at what card 1 will do. So C1 initially will be at root node. It can go to this node, right? Because it has two units of fuel. Okay. So after reaching here, the amount of fuel get reduced one by one. So now K will be 1. So it can go to here. It can go here, right? Now K will become 0. So now it needs to get refillment. Okay. It can, as we saw before, it needs to get refillment from the nearest node, right? So the first point is here. So this is the first point where in which the card gets out of fuel. So now it requires fuel from any of these nodes, because both of the nodes are at the shortest distance. So it can ask for refuelment, and then once it gets the refuelment, it can, let's say it goes towards this way. It goes to this way again. K will become 1, because after getting refuelment, the tank will get filled again. Now K will become 1 after reaching this node. After reaching the end node, the K will become 0, but that doesn't matter because we have reached a leaf. Okay. So what will happen if we have another node here? We have another node. We have to again request for refillment, right? Because K is 0 at this node. So at this node, we are again requesting for refillment. So after getting K equals to 2, K will become 1, and we will reach the leaf node. Okay. So if we just see the whole path of the tree, if you just see the whole journey of C1 from root node to the leaf node, how it goes, you can see here in the path it requests for refillment 2 times, right? 2 times, once at this node and once at this node. Okay. So let's see where let's see if we can predict at which nodes it will request for refillment, right? Okay, let's see. So as I said before, when we request for refillment, we need to find the shortest, we need to find the nearest leaf node, and then we need to request for refillment from that node, right? So at any point of time, at any node, we need to have the information about the shortest nearest leaf node. Okay, so that's one thing. Nearest leaf we need to find, and then let's see. So in order to as we saw in the initial problem, when the amount of petrol, when K is infinity, the answer was just the amount of time it took the car to just reach the leaf node, right? So in that case, it will be 1, 2, 3, 4, 5. So 5 is nothing but the distance of the leaf node from the root node. So in that case, we just need to add the distance of all the leaf nodes. If in case of K not equal to infinity, what will happen is refillments will happen, and the answer will increase. Answer will get increased by some delta, right? So answer is still the distance of all leaf nodes, but then we have to add it with some amount of time. So this amount of time is nothing but the amount of time it takes. This is the refillment time. So you can see here, if there is no refillment, it can reach 1, 2, 3, 4, 5. In 5 steps, the car can reach the leaf node. But since we have refillment, it will take some more time. That time is delta, and that time is nothing but whenever refillment happens, the amount of time it takes for refillment is nothing but the distance between the current node and the nearest leaf node, right? So that amount of time, if you just ask me what is the time which it takes for this node to get refilled, it is nothing but the distance between this node and its nearest leaf node, which are these 2 nodes, but we can take any one. Similarly here, the amount of time it takes for this node to get refilled is nothing but the distance between this node and its leaf node. Okay, so we need first we need to find the nearest leaf node. Also, we need to maintain the distance from I to nearest leaf node. Okay, so if we have these 2 information, we can easily find that we can easily find the delta, because so answer of leaf is nothing but distance of leaf plus refuelment time. Refuelment time we can find with these two values, right? So if you let's just assume we have these two values and start the whole process again, and we'll do DFS, and we start from root node and we go. Now we come here. After we come here, let's say we somehow got the value of nearest leaf. Okay, we know this is the nearest leaf, and we also know this value, distance between I and nearest, distance between current node and the nearest leaf node. We add that to the value and we go, and we reach the leaf node, and we add the whole refuelment time along with the distance to the answer, and we move on, right? But is it possible to do what I just said in a single DFS call? See, once we come here, we don't know where the car is going to. The car can either go here, the car can either go here, the car can either go here, right? Because in DFS can visit any of its child node. So in that case, we can't. We have, even though if we have the refuelment time, we don't know to which leaf node we will add this. We will add this refuelment time to. We don't know which leaf node, because we don't know which order we will go, right? And if we just know how DFS works, after reaching this leaf node, it won't go back again to the root node and then start coming here, right? Because that won't happen, because after in the backtracking step, after it reaches this node, it will backtrack. After reaching this node, it will again go to its child node, and then it will backtrack and not revisit. Okay, that's to be noted. So no way we can simulate the whole process for each leaf node. Okay, so that's another thing to note. So hence in a single DFS call we can't do anything. So we need at least 2 DFS call in order to solve this problem. So let's see how to do this. So the implementation part was a bit tricky also. Like initially it was not obvious to me as well. Okay, let's see. Yeah, so if we just try to solve like how we discussed till now, it won't be possible, because we can't again view the problem from car's side, right? We have, as I said before, we have to see the problem from leaf's point of view. If you see the problem from leaf's point of view, once you reach this leaf, you know there should be a car, right? Some car has reached this leaf. Okay, when during DFS some car has reached this leaf. Okay, now you will see, I know the distance between a leaf and root node. Okay, now you will try to compute this value, this delta value somehow. We'll see how to do that. Okay, similarly, when you reach this node, you know this is a leaf node, and you will try to predict this delta value, right? Okay, so, okay, now now the only thing that's left to do is predicting the delta value. Right. One second. Yeah, 1, 2. Yeah. Now the only thing which is remaining is predicting delta value. So we saw here, if k is 2, the car requested for refillment at this node and at this node, right? So the delta value only depends upon the refillment spots, right? If we know where the car requests, for any car where it requests for refillment, we can easily find the delta value using those two values which I wrote before here, right? So we know here it requests for refillment, but can we observe something? Can we see some pattern in the refillment spots? Like since k is 2, can we see some pattern here, right? Like we have a distance array, right? And initially the distance of root node will be 0, and distance of this node will be 1, distance of this node will be 2, distance of this node will be 3, distance will be 4, and distance will be 5. Is there a pattern here using which we can predict the refillment spots. Yes, right, because you can see here, since k is 2, the car will always request for refillment after reaching the kth node, right? In k gaps of interval, right? If we have a straight line, if it car starts at 0, after making 2 steps, it will request for refillment at 2, right? And after again getting refillment, it will again request for refillment at 4th node, right? So all nodes which has distance modulo k as 0 will request for refillment. So this is the most important observation to make here. So this information itself will help us solve the problem in given within the constraints given. So whenever the distance of any node is modulo k is 0, there will be some car, whenever a car reaches that node, it will request for refillment. Okay, now the problem is somewhat reduced. Okay, so let's say we just, if we once we reach the leaf node, we saw that answer of leaf is just nothing but distance of leaf plus this delta, right? So this delta is nothing but summation of refillment time for all refillment spots, you can say this. So delta is nothing but summation of refillment time for all refillment spots. In this case, it will be the refillment time of this node and this node for this leaf node. For this leaf node, it will be just the refillment time of this node. Okay, so if you have some idea of backtracking, you can easily observe that we can easily do this with backtracking if you just have we just maintain an array or vector of refillment spots, refillment stops, right? If you just have a vector stops, and whenever you meet a point which is a refillment spot, you just put it into a vector. Yes. In the backtracking step, the DFS step, you will have stops, and if the current node is a stop, you just put it inside the stop and you go and you continue the process, right? So after coming here, the spots, the stops vector will have this node 1 2 3. Let's call this node as 3. It will have 3 and 4 5. It will have, after coming here, it will have 3, 5. So this is the refillment spots, right? So when we reach this leaf node, when we reach this leaf node, we know we got to know about the refillment spots, right? Now it's just a matter of time before we find the summation of refillment time. Okay, so how to, okay, if we have the refillment spots, now we just need to add the refillment times of all those refillment spots, right? So from where we can get the refillment time? So the refillment time is nothing but, as I said before, it's the distance between the current node and its nearest leaf, right? So if you somehow store that value for all the nodes in the tree, when you have the node value, you can easily get the refillment time in constant time, right? If you already stored, if you just pre-compute the whole value, value, which is nothing but nearest distance between node I and the nearest leaf. If you store this for each node, it will be easy for us when we reach leaf to get the value for each stopping point in order of one time, right? Because you already stored it somewhere. So the algorithm will go like this. So initially we'll do a depth first search and find out all the distances between each point. Distance of I we will find, and then we will find the distance between I and nearest leaf. So this is nothing but, if you see here, this is nothing but the shortest path length in the subtree of node I, right? This is 1. So if you see for this node, this is nothing but the shortest path length in its subtree. So you can say this is shortest path length in subtree of I. If we find these two values in the first run of DFS, in the second run of DFS, what we can do is, whenever we reach the leaf node, we have the stopping points. So we get all the stopping points, we add these two values and find the answer. That's it. The problem is solved. So you can see here we are just making 2 DFS calls, and each DFS calls will take order of n plus e. DFS, the time complexity of DFS is n plus e, which is in this case e is n minus 1 because given graph is a tree. So the total time complexity will be order of n, and yeah, space complexity will be order of n again because we need to store these two values in arrays. So we'll be using the same logic to solve the problem. Okay, yeah, let's look at the code. Okay, this problem, yeah. So k will be given to us, and this is the adjacency list. We'll be representing the tree as an adjacency list, and then this is the distance array, and then I am using one more array to just know whether the given node is a leaf node or not, and then this DP array is nothing but the one which I said shortest path to leave this thing, the shortest path length in the subarray. So DP array represents that, and then sums is the extra travel. Okay, sums is nothing but this refillment cost for each node. So since we need to do that for each leaf node, I am just storing it in another array. And then since our problem is returning long, I am just declaring a long vector instead of integer vector in order to avoid any more overflow issues. Okay, so as I said, we'll make 2 DFS calls. Let's see. So this is the solve function. First we need to initialize all the vectors, and then as I said before, parent of I is -1, it will represent a root node. So in order to perform DFS, we need to know the root node. So initially let's assume root node is -1 and then go through the entire process. After finding the edges, if v is -1, parent of I is -1, I is root node, and add it to the adjacency list. And once you find the root node, do the first DFS. It should be nothing but in the first DFS, what we will do is, as I said before, first DFS we'll find these two values. The second DFS we'll just add the values and find the answer for each leaf node, right? Leaf node. So in the first DFS, we need the current node to do DFS, and then we need a parent node. Along with it, we need a d value which will just represents the distance to current node. So distance of node will be d, and then we'll go through its adjacency list, and if its adjacency list contains an element which is not a parent, then which means the current node is not a leaf, right? So initially we'll assume all nodes are leaf. So we can see here, initially we have assumed all nodes are leaf, and then once we meet a node which has some elements which are not in its adjacency list, which is not its parent, we'll declare the node as not leaf. And then we need to find, this minimum represents the shortest path length in its subarray. So we'll make a DFS call. So DFS will return the shortest, so DFS of node will return the shortest path length in its subarray of node. So we'll take the minimum of those values, and DP of node, which is nothing but the shortest path to leaf, will just be, if it's a leaf node, there's no need to find the shortest path length, because once we reach the leaf node, no need for refillment, right? Because we already reached the leaf node. So shortest path length in its subarray will be 0. If it's not a leaf node, it will be minimum. And then we need to return 1 plus DP node. So this 1 plus is required because when we backtrack and go to the parent node, we need to add 1, because the 1 represents here, for example, let's see, when we are here, this is a leaf node, right? So DP of leaf will be 0, and when it backtracks to its parent node, it should return 1 plus DP of node, because if it just returns DP of node, it will be 0 again. And then here, if it takes minimum of these 3 values, it will say it's 0, and then it will again return 0, and the whole tree will have incorrect values. So we have to add 1. So that 1 represents this edge movement. We have to make one more edge, one more movement. That's what the 1 represents. And then so this DFS computes the distance array, and then the DP array. It fills both of the arrays, and then once we do that, as I said before, we will maintain a stops vector to know where are the refuelment stops. These stops which are highlighted in red color. So yeah, after that we'll make another call to DFS2. So DFS2 is nothing but the same way we do the previous DFS, but so once we find a node which has a positive distance, so yeah, this thing I have added because you can see here root node's distance will be always 0 and 0 modulus k will be always 0. So but that's not the case, right? Because k is given as positive. So what is it? Yeah, k is positive, so k will never be 0. So in order to avoid that, we need to add this case. And then if distance of node is distance of node modulo k is 0, we'll push the node to the stops list, and then we'll make DFS call to its child node. And this is backtracking step we need to. So once here we'll have in this node here we'll have 3,5, right? So here we'll have 3,5. So after reaching leaf, if we are just backtracking, if we go to this step, we shouldn't have 5, right? Because we are at this step, and the total number of the refillment stops here should be only 3. So in order to do that, we need to pop back the recently added one. So after making the DFS call to its child, while backtracking, we need to remove the recently added item. So that's how backtracking works, right? So we need to pop back the recently added one, this one. After that, after that, in the end, if the current node is a leaf node, as I said before, we just need to add the sums array is nothing but sums array is this refillment value. So we will increase the refillment value by dp of stop. So for every stop, for every refillment stop, for every refillment stop, we'll add the refillment time. So refillment time is dp of I, and the stop is node, so it will be sums of leaf plus equals dp of stop. So for each leaf, we'll add the refillment time of all the stopping points in that leaf. So after doing this, initially answer will be 0, and for every leaf node, as I said before, that the answer of I is nothing but distance of leaf plus refillment time, which is exactly what I have written here. Distance of I plus refillment time is sums of I, and we need to find the maximum of those values, because after maximum only all leaf nodes will have at least one car at its position. So we need to take a maximum, and we just return the value. So this is the whole implementation of the solution. And we need to do 2 DFS call. Time and space complexity is linear, and it will easily pass in with the given conditions. As you can see here, it passed, and solution passed. So yeah, that's it, I guess. Similarly for B also, the solution passed. Similarly for the first problem, the solution passed.